Now we're going to look at the trends in the first ionization energy, the periodic trends in the first ionization energy. Right? So those are the trends um, down the group as well as across the period. Before we do that, we're just going to talk about the factors that affect ionization energy. Okay, factors affecting ionization energy. Right. So over here, the first factor that affects ionization energy, right, is the nuclear charge. Right, that is the number of protons in the nucleus. Right, we know that ionization energy is always endothermic, right, and a greater nuclear charge would mean a more endothermic ionization energy, right, because ionization energy, or specifically the first ionization energy, is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms, right, to form 1 mole of 1 plus gaseous ions. So essentially, right, this is, we're trying to determine how difficult it is to remove the electron from an atom, right, or an ion. So the greater the nuclear charge, the more endothermic, the more difficult it is to remove an electron, right? We have shielding, right? Now when we talk about shielding, that is repulsion due to inner electrons, right? Shielding refers to repulsion due to inner electrons, repulsion due to inner electrons, right? Now previously we've only looked at shielding due to, for example, we looked at shielding due to inner shells, right? We said that electrons in the second shell are shielded by electrons in the first shell, right? But you also have shielding within the same shell. Inner orbitals can shield outer orbitals, right? So for example, s orbitals can shield p orbitals, right? Because p orbitals are further away from, electrons and p orbitals are further away from the nucleus. Electrons and s orbitals can actually repel them. Okay, so here we're going to talk about not just due to shells but also because of different subshells. Okay, orbitals or subshells. Okay, so orbitals in different subshells can, an orbital in a lower subshell, right, at a lower energy, can shield an orbital at a higher subshell or at a higher energy. Obviously, the greater the amount of shielding, the easier it is, right, to remove that electron, so the less endothermic the ionization energy. Then we have radius, right, or size of the ion or the atom, right. The again, radius is a measure of the radius is just the distance of that outer electron from the nucleus, right. Greater radius means that outer electron is further away. A greater radius would mean lesser energy is needed, and a smaller radius, if the outer electron is closer, more energy would be needed, right. And then the last factor that we're going to discuss is spin pair repulsion. If you have paired electrons, the electron is easier to remove. If they're unpaired, they're harder to remove, right? So when you have a spin pair, the ionization energy you would expect it to be less endothermic. So now let's look at the trend in the first ionization energy as we go down the group. Okay, so let's say that we have group 1 here, for example, right? And we have lithium, sodium, and potassium, right? And the question is, what happens to the first ionization energy as we go down the group? We know that down the group, okay, down the group, the first ionization energy becomes less endothermic. Okay, the first ionization energy, okay, becomes less endothermic, right? Or we can say decreases. Okay, we can say it decreases down the group. Okay, decreases, or we can say becomes less endothermic down the group. Right? And the reason why, it's the exact same explanation as we had for radius, right? The same idea. We know that down the group, the number of shells increases. Number of shells increases. Hence, we know that shielding increases, right? That is repulsion due to the electrons in the inner shells, right? Increases. So we know that hence shielding increases, right? And the outer electrons are further away from the nucleus, right? The outer electrons are further away from the nucleus, right? In other words, the radius is increasing, right? All of this means that therefore we can say that the outer electron are less, right? Or we can say that the outer electrons are less strongly attracted to the nucleus, and lesser energy is needed to remove them. Lesser energy is needed to remove them. So this is the idea, right? What we see is that the ionization energy, the first ionization energy, becomes less endothermic down the group. Okay, and this is true for any group, right? So you would see that, for example, iodine, right, has a first ionization energy that's less endothermic than bromine, which is lesser than chlorine, and so on, right? So when you go down any group, the first ionization energy will become less endothermic, or it will decrease. Over here, especially for the group 1 elements, okay, for the group 1 elements, okay, it's also a measure of reactivity. Okay, it's also a measure of reactivity, right? We know that because potassium has the lowest ionization energy, or the lowest first ionization energy of the three, right, among lithium, sodium, and potassium, right? It implies that it is the most reactive, right? It loses its outer electron most easily, right? And therefore it is the most reactive. So for the first ionization energy specifically, right, it's also a measure of reactivity of group 1 elements, right? Because we talk about group 1 elements, they tend to just lose their outermost electron, right? Just that first electron. And what we're saying is, because this has a less endothermic ionization energy, it means that this guy is going to lose its outer electron more easily, and therefore it is more reactive as a reducing agent. Okay. And just to clarify that this trend, okay, of decreasing ionization energy down the group applies to any group. Okay, it applies to all the groups that you guys learn about, group 1, 2, 13, 14, 15, 16, 17, right, and 18. Right, as you go down the group, it becomes less endothermic, the first ionization energy. Okay, and again, as far as the reactivity is concerned, if you're looking at just first ionization energy, you're talking about group 1, right, in terms of if you want to look at it as a measure of reactivity. For group 2, it's the first and the second, right, and so on. And obviously, as far as ionization energy as a measure of reactivity is concerned, right, it only applies to cations. It wouldn't apply to anions, right? Because when we talk about reactivity of anions, right, those are gaining electrons, whereas ionization energy specifically refers to the loss of electrons. Another thing to note here is that down the group, the nuclear charge is increasing. However, this increase in the number of shells, the increase in shielding, and the increase in the radius outweigh. Okay, this outweighs the increase in nuclear charge. Okay, outweighs the increase in nuclear charge. Now, if you look at the trend in the first ionization energy across the period, so let's say we're looking at period 3, right? If we look at period 3, we have sodium, magnesium, aluminum, silicon, right, phosphorus, sulfur, chlorine, and argon, right? So across the period, right, the first ionization energy becomes more endothermic. So we can say that the first ionization energy increases or becomes more endothermic, okay, across the period. Okay, And the idea is the same as we had for radius, right? Across the period, the number of shells remained the same, shielding remained the same, but the nuclear charge was increasing, right? Which meant that the radius became smaller and the outer electron is harder to remove. So the ionization energy is increasing or becoming more endothermic. Okay? So what we can say is that the nuclear charge increases. The nuclear charge increases across the period, right? As the number of protons increases, whereas the number of shells, right, and therefore shielding remain the same, right? This means that we can say that hence the outer electrons experience greater attraction from the nucleus, okay, or experience greater nuclear attraction, and more energy is needed to remove them. More energy is needed to remove them. Okay. This is the general trend. This is the general trend in the first ionization energy. Okay. There are exceptions to this trend. But this is the general trend in the first ionization energy across the period. So here's a graph that shows the increasing trend, right, across the period in the first ionization energy. Okay. So we have a generally increasing trend. As I mentioned, this is a general trend across the period, but there are exceptions to this trend, right? We see that the first ionization energy decreases. It decreases as we go from magnesium to aluminum. And we also see that the first ionization energy decreases from phosphorus to sulfur. So the question is, why do we see these exceptions, right? Why do we see these exceptions in the first ionization energy trend across the period? Okay, so if we're asked to explain what explains this, for example, from sodium to magnesium, or from, let's say, sulfur to argon, right, we have this generally increasing trend, right? So that's just the general trend, right? The nuclear charge is increasing, the number of shells is the same, right? So if you're ever asked to just explain any of the increasing trends, right, that's just the general trend. Or you're asked to explain the general trend, we've already learned that, right? Nuclear charge increases across the period, number of shells and shielding remain the same. So nuclear attraction towards electrons increases and more energy is needed to remove them, right? So now we're going to answer the question as to why we see these exceptions, right? And if we look at this in more detail, what we see is that we don't just see these exceptions in period 3, right? We're seeing it from magnesium to aluminum and phosphorus to sulfur. We see that decrease in period 3, but we also see this exception in period 2, right? So if you look at this graph here, we can see that it's decreasing from beryllium to boron as you go across the period, right? The first ionization energy is increasing. That's the general trend, right? But we see that it decreases from beryllium to boron, and it also decreases from nitrogen to oxygen. Similarly, if you look at the third period, right, this is the third period, what we see is it's increasing from sodium to argon. That's the general trend. But again, you see a dip from magnesium to aluminum and phosphorus to sulfur. So here you have two classes of exceptions, right? So what are the two exceptions in the trend, right? We have exceptions in the first ionization energy trend across the period, right? Across the period. And the two exceptions that we see are when we go from group 2 to group 13, right? Those are the exceptions highlighted here. When we go from beryllium to boron, or when we go from magnesium to aluminum, we see a decrease in the first ionization energy. And the other exception that we see is from group 15 to group 16. That's the decrease that we observe when we go from nitrogen to oxygen or from phosphorus to sulfur, right? Nitrogen is in group 15, oxygen is in group 16. We see a decrease, and same thing for phosphorus to sulfur, right? Group 15 to group 16, we see a decrease in the first ionization energy. So these are the two exceptions. Okay, and we're first going to look at the exception that we see from group 2 to group 13. Okay, And what we see from group 2 to group 13, right, is for example, if we were comparing the first ionization energy of magnesium versus aluminum, right, we know that we can clearly see that aluminum has a lower first ionization energy. Okay, it has a lower first ionization energy than magnesium, right? Now the question is why. Now if we look at the configuration of magnesium, right, you know that magnesium has a configuration of neon and then 3s2, right? This is the configuration of magnesium, right? It is neon and then 3s2. This is just a short form, right? So this is the configuration of magnesium. And if we look at the configuration of aluminum, the configuration is neon and then 3s2 and then 3p1, right? So here we have aluminum, we have neon, and then we have 3s2, and then we have 3p1, right? Which is at the p subshell is obviously at a higher energy, right? So we have 3p1. Right, now what happens is that what we see here is the following, right? What we see is that if you look at magnesium, the 3s electrons, so the electrons in this 3s orbital are being shielded. In other words, they're being repelled from the inner electrons, right? That these 10 electrons that we have here, right? 1s2, 2s2, 2p6. There's 10 electrons that are shielding these outer 2 electrons in magnesium. Whereas in aluminum, right, you have the same 10 electrons shielding this outer electron. However, in addition, you also have electrons in the 3s subshell, right, in the 3s orbital. In a 3s orbital, these electrons are shielding the electrons in the 3p orbital. Okay, because these electrons on average are closer to the nucleus, right? So they actually end up repelling these electrons in the 3p orbital. Okay, so there's additional shielding. Not only are these 10 electrons shielding the outer electron, in addition, the electrons in the 3s orbital are also shielding this outer electron, which is why you see a dip. So the idea here is that we know that as we go across the period, the nuclear charge is increasing, right? Which means that outer electrons are becoming more difficult to remove, right? The first ionization energy is increasing because the nuclear charge is increasing. The number of shells is the same, right? But what we see is that from magnesium to aluminum, right, even though the nuclear charge is increasing, this additional shielding actually outweighs that increase in nuclear charge, right? You go from a 12 protons in the nucleus to 13 protons in the nucleus, right? And what happens is that despite the nuclear charge increasing, because of this additional shielding in an aluminum atom due to the 3s electrons, right, of shielding of the 3p electrons due to the 3s electrons, this additional shielding causes a decrease in ionization energy. Remember, the more they're being repelled away from the nucleus, the easier they are to remove, right? But then as the nuclear charge increases further, then this additional shielding effect is overcome. Okay, so that's why you still see that consistent increasing trend after aluminum. So what we can say over here is that the reason we see this decrease in the first ionization energy from aluminum to magnesium is because we can say that the electrons in the 3p orbital, right, in the 3p orbital of aluminum, right, experience additional shielding due to the electrons in the or from the electrons in the 3s orbital, right? And this 3s orbital we know is closer to the nucleus, right, which is closer to the nucleus. So then that means that here in this case, because of this additional shielding, hence we can say that the nuclear attraction, right, nuclear attraction towards the outer electron decreases and lesser energy is needed to remove it. The exact same explanation would apply to the trend that you see from beryllium to boron as well. Okay, so this highlights the trend from group 2 to group 13. Okay, from beryllium to boron or from magnesium to aluminum. Obviously, if you were talking about boron having a lower first ionization energy than beryllium, right? Here, obviously, you'd have additional shielding of the 2p electrons from the 2s electrons, right? So it's from magnesium to aluminum, you have additional, in the aluminum atom, you have additional shielding of the 3p electrons, right, by the 3s electrons, whereas in boron, you have additional shielding of the 2p electrons by the electrons in the 2s orbital, right? This is just in the lower shell, right? But the idea is the same. The p electrons are being shielded by the s electrons, which means that you have a decrease in ionization energy here. But then the further increase in nuclear charge then overcomes that additional shielding effect. So then you see that increasing trend afterwards. So this explains why the first ionization energy decreases as you go from group 2 to group 13. Okay, or from group 2 elements to group 13 elements. Right? Now we're going to look at the next exception, right, which is we see a decrease in the first ionization energy as we go from group 15 to group 16, right? So here we're going to try to answer the question, right? Why does phosphorus have a greater first ionization energy than sulfur, or why does sulfur have a lower first ionization energy than phosphorus, right? So we can clearly see here that sulfur, right, the first ionization energy of sulfur, the first ionization energy of sulfur is lower than phosphorus. So now if we look at the configuration of sulfur versus phosphorus, right, we can see that the configuration of phosphorus is neon and then 3s2 3p3, right? It ends in p3, it's in group 15, and the configuration of sulfur is neon and then 3s2 3p4. So now if we just look at the p orbitals here, or we look at the p subshell, right, we see that in a phosphorus atom, right, all the electrons in the p subshell are unpaired, right? Each of the p orbitals has a single electron. Now in a sulfur atom, we have this configuration ending with 3p4. So in the 3p subshell, again we have three different p orbitals, right? And what we see is that one of the orbitals has a pair of electrons, right? One of the orbitals has paired electrons. And we've learned previously that when we have electrons in the same orbital, right, they repel each other, right? So over here what we have is spin pair repulsion, right? Spin pair repulsion. You can also say electron-electron repulsion or inter-electronic repulsion, right? They all mean the same thing. The two electrons are repelling each other. So because of this repulsion between the electrons, right, because of the spin pair repulsion, it means that this electron is easier to remove, okay, and from the sulfur atom than it is in the phosphorus atom, the outer electron. And again, when you form the 1 plus cation in this case, after the first ionization energy, when you remove the first electron, right, it's going to be this paired electron that's removed, okay. So what we can say over here is that one of the 3p orbitals, right, one of the 3p orbitals in an atom of sulfur, right, consists of a electrons, pair of electrons, and because we have paired electrons, in this 3p orbital, right, what we can say is that we can say therefore the outer electron, right, experiences spin pair repulsion, right, experiences spin pair repulsion, or you can say electron-electron repulsion or inter-electronic repulsion. right? Hence, it's easier to remove. Hence, lesser energy is needed to remove it. Okay? Hence, the nuclear attraction towards outer electron decreases, and lesser energy is needed to remove it. Okay? Again, it'll be this paired electron that's removed first. Okay, and we know that this p3 subshell configuration, right, in phosphorus is more stable, right? This the half-filled P3 configuration in phosphorus is more stable than this partially filled P4 configuration in sulfur. Okay, so the half-filled P3 configuration is more stable, right, than the partially filled P4 configuration. Now we see the exact same decrease from nitrogen to oxygen as well, right? Because we're going from group 15 to group 16. So we know that the first ionization energy of oxygen is lower than nitrogen. Okay, and the reason why is in the case of oxygen, right, we have a 2p4 configuration, right? In sulfur we had 3p4, and oxygen we had 2p4, right? Whereas in phosphorus we had 3p3, this is 2p3, right? But the idea is the same, right? In the oxygen atom, because we have a 2p4 configuration, right? One of the 2p orbitals in an atom of oxygen, right, consists of a pair of electrons. The outer electron experiences spin pair repulsion, and nuclear attraction towards the outer electron decreases, and lesser energy is needed to remove it. Okay, so again, the half-filled P3 configurations, in nitrogen and phosphorus atoms are more stable than the next element in the periodic table for each of these respectively, which are oxygen and sulfur. So the following graph summarizes the trends that we've learned for the first ionization energy, right, down the group as well as across the period. We can see the trends down the group here, right? We know that over here we can see that potassium has a lower first ionization energy than sodium, which has a lower first ionization energy than lithium, right? So these are your group 1 elements, right? These are your group 1 elements right here, and we can clearly see the decreasing trend down the group, right? We see a very similar trend see the same trend for group 2, right? We go from beryllium to magnesium to calcium, right? Again, this is group 2. You see the same decreasing trend down group 18 as well, right? If you look at helium, argon, neon, and then argon, right? So in this graph, we can clearly see the trends down the group, right? Similarly, we can see the trends across the period, right? We can see that the first ionization energy increases across the period. That's the general trend, right? So it decreases down the group because the number of shells increases, right? And shielding increases, and the outer electrons get further away from the nucleus. So it's easier to remove them. Lower energy is needed. Across the period, number of shells remains the same. Nuclear charge is increasing, so more energy is needed to remove the outer electrons, right? Because nuclear attraction is increasing. You also see the exceptions, right? When you go from beryllium, the outer electrons are 2s2, the configuration, right? These are the highest energy electrons are in the 2s orbital, and then for boron it's 2p1, right? So when you go from 2s2 to 2p1, right, this is the highest energy electrons. The highest energy electron in boron are in a 2p orbital. Similarly, so that's group 2 to group 13, and you see the same thing in this third period when you go from magnesium to aluminum, going from the outer electrons being in a 3s orbital to the outer electrons being in a 3p orbital, right? Again, if you're going across the period, again, right, boron, carbon, nitrogen, you have the same increasing trend. Oxygen, fluorine, neon, you have that increasing trend. But from nitrogen to oxygen, you have a decrease because you're going from 2p3 to 2p4, right? And then phosphorus to sulfur, you're going from 3p3 to 3p4. So here you have spin pair repulsion, right? So it's easier to remove the outer electrons from oxygen and sulfur relative to nitrogen and phosphorus respectively. Another thing that you observe here is that in any given period, right, obviously we're not looking at period 1 here, which is hydrogen and helium. If you look at the rest of the periods, in any given period, the lowest first ionization energy will always be the group 1 element, and the highest first ionization energy will be the noble gas, the group 18 element, right? So it's increasing across the period, and then obviously you're moving on to the next period, so you've increased the number of shells, so there's a huge decrease. And again, the group 1 element will have the lowest first ionization energy in the period, and the group 18 element will have the highest, right? Group 1 element has the lowest, group 18 element has the highest first ionization energy across the period. So the next question we want to answer here is, why do the first ionization energies remain relatively constant across these d block elements, right? So if you notice, from scandium to copper, right? Scandium is atomic number 21 and copper is atomic number 29. We see that the first ionization energy remains relatively constant, right? So what we can say here is, I'll put a star here, right? What we can say is that the first ionization energy remains relatively constant from scandium to copper. Scandium has atomic number 21 and copper has atomic number 29. So if we look at the d block elements here, right, what we see is, right, we know that scandium has the configuration, right, argon and then 3d14s2. Then we have titanium, right, which is argon and then 3d24s2, right? Then we have 3d34s2, then 3d54s1, and so on, right? What's happening is that we're increasing the number of electrons in the d subshell, right, or the number of electrons in the d orbitals, right? Now normally electrons are added to the outermost shell. Okay, normally electrons are added to the highest energy levels of the outermost shells, but in this case what we're doing is the outermost or the highest energy level is the 4s sublevel here, right? The 4s orbital is the highest energy orbital. So what we're doing is we're adding electrons in the inner d subshell. So normally when you go down the group, for example, right, we increase the number of shells and shielding increases. Here shielding is increasing because the 4s electrons are being shielded by the 3d electrons, okay? However, the number of shells isn't increasing. So what we see is that across these elements, right, from scandium to copper, right, what we see is that the shielding is increasing, but the shells aren't, and the nuclear charge is also increasing. Exactly. So the increase in nuclear charge actually balances the increase in shielding. Okay, so the first ionization energy remains relatively constant. So again, the idea over here is that across these elements, right, if you go from scandium to copper, right, you're increasing the number of electrons in the inner 3D subshell, or in the inner 3D orbitals. These are at lower energy than the 4s orbitals, right? But you're not increasing the number of shells. So what's happening is the nuclear charge is increasing, right? So the nuclear charge increases, right? However, this increase in nuclear charge, is balanced by the increase in the electrons, or the number of electrons in an inner or lower energy d subshell. So we can say that the number of electrons in the inner 3D orbitals, right, or 3D subshell increases, right? Therefore, we can say that the outer 4s electrons are more shielded, right? Are more shielded, As a result, as a result, right, the overall nuclear attraction, the overall nuclear attraction, overall nuclear attraction remains relatively constant, right? The overall nuclear attraction towards outer electrons, outer 4s electrons remains relatively constant, right? So what's happening here is that the nuclear charge increasing means it's harder to lose an electron. However, the shielding increasing means that it's easier to lose an electron, right? And the two changes actually balance each other out. So what we can say here is that the increase in nuclear charge, is balanced out by the increase in shielding due to the number of electrons in the inner or lower energy 3D subshell, right, or the lower energy 3D orbitals increasing. So this increase in shielding and the increase in nuclear charge cancel each other out, and therefore the overall nuclear attraction towards the outer electrons remains relatively constant, or we can say that it remains similar. Okay, it remains relatively constant or similar. This actually also explains why the atomic radius remains similar or relatively constant from scandium to copper as well, okay? Because the shielding and the increase in shielding and the increase in nuclear charge balance each other out, or they cancel each other out. The first ionization energy remains relatively constant, and the atomic radius also remains relatively constant. So the exceptions that we learned about, okay, one thing I want to clarify here is that if you look at the exception from group 15 to group 16, for example, right, what we have is we have spin pair repulsion, right? We have spin pair repulsion when we go from P3 to P4, right? So group 15 to group 16, that's nitrogen to oxygen or phosphorus to sulfur. And although it is implied, in recent exams, they want you to explicitly mention that this spin pair repulsion outweighs the increase in nuclear charge. Okay, the spin pair repulsion outweighs the increase in nuclear charge. Okay, it outweighs the increase in nuclear charge. Now again, this is implied. The reason is implied is because we know that the general trend, across the period, very similar idea applies to the other exception that we learned about, which was from group 2 to group 13, right? Here what we saw was a decrease in the first ionization energy from group 2 elements to group 13 elements, and that was because of electrons in the p orbitals experiencing additional shielding from electrons in the s orbitals. Again, this additional shielding outweighs the increase in nuclear charge. Okay? So explicitly mention that if you're asked to explain these exceptions, right? It outweighs the increase in nuclear charge. So then what we can say is that when we go from group 2 to group 13, the additional shielding of the electrons in the p orbital by the electrons in the s orbital, right, outweighs the increase in nuclear charge. Whereas when we go from group 15 to group 16, right, the spin pair repulsion of the electrons, right, in the p orbitals of the group 16 elements, right, means that the first ionization energy of these group 16 elements is lower than the first ionization energy of the group 15 elements. Okay, this spin pair repulsion outweighs the increase in nuclear charge. So to summarize, there are essentially three exceptions in the first ionization energy, right? When you go from group 2 to group 13, right, where the increase in shielding from s electrons, right, the increase in shielding due to s orbital electrons, right, of the p orbital electrons outweighs the increase in nuclear charge. From group 15 to group 16, where the spin pair repulsion in the p orbital of group 16 elements, right, means that first ionization energy decreases, and this outweighs the increase in nuclear charge. And then across the d block, right, from scandium to copper, where we don't see an increasing or we don't see a decrease or a very obvious increasing trend. We see that it remains relatively constant, and here the shielding and the nuclear charge balance each other out or cancel each other out.